In this video, we're going to talk about model assessment and various strategies for model selection. So one of the basic questions that you might ask yourself is flexibility of a model better? For example, for polynomials, the higher degree that we have, the more flexible the polynomial. As the degree increases, the graph of that polynomial becomes bendier. This data set is going to be a helpful data set to help us reason through how much flexibility we may want in a particular model. I note here just in the beginning that we have n equals 21 observations. So to begin, we may fit a linear regression model just using simple linear regression, a degree 1 polynomial, and this is what it would look like. Obviously, it's a terrible fit. The residual sums of squares there is 9.17, and this model is not helpful to us at all. So maybe the question should be, well, maybe I should dial up the degree on the polynomial and find a degree that I like, since degrees correspond to flexibility as far as polynomials are concerned. Here's a degree 2 polynomial. This is a quadratic resulting in a parabola, and again we see a really poor fit. So maybe we should just go further. Maybe a cubic is better. Here's what the cubic looks like. Notice that the residual sums of squares is decreasing a little bit. So now it's 7.6 or so. And the fit still looks just visually pretty poor. So we would probably keep going. Here's a degree 4 polynomial, and things are starting to look significantly better. The residual sums of squares took a major drop, and the line generally fits the pattern of the data. But since we've gone this far, we might as well try going further. Maybe the residual sums of squares will keep coming down. So it's 1.75 right now. Here's a degree 5 polynomial. That's 1.39. 6 is 0.86, so we see another drop there. And we can just keep going down. 7, 8, 9, 10. Notice now the residual sums of squares has continued to decrease. We notice that we're actually hitting both of the points on the endpoint. So our line appears to be going through both of those exactly, and it's kind of wiggling a little bit more on the outside, okay? And we're going to see that continue as the polynomial degree increases as a consequence of something called Runge's phenomenon, okay? So degree 12, degree 13, again, we're seeing the residual sums of squares decrease, and now we're seeing a high degree of oscillation at the boundary values, okay? And that will continue to increase as we see that more and more erratic behavior. Remember that even degreed polynomials eventually have to go either both up or both down on the sides, and odd degrees have to go alternate ways. So one will go up and one will go down eventually. So here we have 16, they're both going up on the sides, 17, one's going up, one's going down, and then in the middle, we're starting to match more and more points, okay? Here's 18, here's 19, and now it looks like we've almost gone through every single point, and here's 20. So if we actually fit this data with a degree 20 polynomial, remember we had 21 points to begin with, the residual sums of squares is 0 because the curve has actually gone through every single point. And in fact, that's a more generic fact that's true. If you have n data points in 2 dimensions, a polynomial of degree at most n-1 will be able to go through all of them. We say at most because it could just happen that those endpoints are all on a line or something like that, and you only need a degree 1 polynomial. But typically you'll need a degree n-1 polynomial. And of course we need to have distinct x's here. So no 2 points can have the same x value. So that seems great. I mean, as the degree increases up to n-1, the residual sums of squares will decrease down. And in fact, we can make a little plot of this. As the polynomial degree on the x-axis grows, that means the flexibility of the model is getting better, and the residual sums of squares is going to decrease. So this may kind of leave you with the idea, well, maybe we should always use an n-1 degree polynomial, right? If we know that an n-1 degree polynomial will always go through all the points, by the way, that's called interpolation. We'll just use a degree n-1 polynomial and we'll interpolate all the points, okay? A different way to think about this is that if you have 2 competing models, let's call one M1 and M2. So maybe M1 is the degree 1 model and M2 is a quadratic model. Is a lower residual sums of squares necessarily indicative of better behavior as a comparator between models, okay? We know that within a particular model, the residual sums of squares is the way that we actually select which coefficients we use. But we haven't really thought about this between different models before. And in fact, these models are in some sense nested, right? A linear model is a quadratic model, just setting one of the coefficients to 0. So This is a way that we should think about flexibility and model selection. I think this is something else that's very useful when we're actually thinking about model selection, which is how does the model do when you predict with that model on new data? So for example, let's suppose that in addition to the points that we saw previously, we now have capital N new points that are of this form. So x1 new, y1 new, all the way up through xn new, yn new, okay? And what we're going to do is we're going to use those new x's and the models that we fit, and we're going to use the models to make a prediction of what the y value should be for those new x's. Remember that when we trained the model, when we fit that model, it didn't actually see this new data. So this new data is totally foreign to the model. It's never seen it before, okay? What we're going to do with that is we're going to make predictions, and then since we have observed new y's as well, we're going to compare those predictions to the new y's, okay? And we're going to compute a residual sums of squares on the new data using the prediction from the model, okay? This is going to be a way for us to kind of measure the error of the model on data that it hasn't yet seen, right? So of course, when we make predictions, we're interested in making predictions on data that we have not yet seen. We're not particularly interested in data that we already have seen, okay? So here's a collection of 21 new observations, and these are scattered all throughout the x's. And our task is going to be to use our models to make predictions for the new red points, okay? Using only the x values of the red points, okay? Now, we're just going to do this visually. So here's the degree 19 model. Remember, the degree 19 model almost interpolates every single point. It misses the points in the middle, but it almost interpolates all of the points. Now, remember how models are selected. Models are selected based on the residual sums of squares, and residuals are defined as the vertical distance from each of the values to the points. So here are some residuals, right? These are the residuals of those particular points. In the middle, we're seeing some pretty big residuals here. Of course, this model has never seen this data before, but the real problem comes on the outside. The real problem comes on points like here on the far left, where it's so large, the residual there would be so large, it's actually going off of the screen. Or over here on the far right, it's so big that way that it would go actually all the way up, and it's way off the screen. So this residual here, even though the model fit the data that it had seen really well, it doesn't predict data that it has not seen very well at all, okay? Let's compare that to something like the degree 6 model, which looks like this. It's a lot less flexible. We know that its residual sums of squares on the training data is actually worse. The residual sums of squares is higher on the training data. However, clearly if we actually look at the residuals, and we can just eyeball this, the residuals on the data that it has not yet seen is significantly better, okay? So generally speaking, in this sense, like simpler models are going to predict better into the future because presumably the relationship between x and y isn't actually a degree 20 polynomial or something like that. That's a very, very complicated relationship, and complexity in some sense just is rare. From here, we can actually add on to the plot that we had before for the residual sums of squares onto the complexity of the model in the sense of flexibility. We can add to that the error for the new training data. Okay, so the residual sums of squares on the new training data. And this is what we get. So the red curve on top, each of those points is going to be the residual sums of squares for a model of that degree on the new data. Okay, so at the beginning it's really poor. In other words, as the model flexibility is something like just a line or a parabola, the model predicts fairly poorly on the data. Okay, but as the flexibility increases, as we get more and more degrees of that polynomial, as we can see at degree 4, there's a big jump in our model performance. And then it gets a little bit better, but not much better as our degree increases. But at some point, when the degree increases beyond it, it just shoots up. So the residual sums of squares is actually so large on the test data that we can't even see it on the screen anymore. Okay? Notice that the highest degree polynomial, of course, is up here. So on the training data goes through every single point. Whereas the residual sum of squares on the data that it has not yet seen, this new data, is just off the charts. It's enormous. Okay, and in fact, this is a general pattern that will hold for models in general in terms of their flexibility on data they have not yet seen. Okay, this is a characteristic pattern that we see many, many times as we're going through statistical learning theory. Okay, the idea is that if you look at the data that the model is trained on, as the flexibility increases, the model error in terms of the residual sums of squares will continue to decrease, because what's happening is as the model becomes sufficiently flexible, eventually it will just fit every single point. Okay? In other situations, we can think about it as the model is memorizing the data set. So its residual sums of squares is very, very low because its recall on that data is perfect. Okay? However, on new data, as the model flexibility increases, it gets better and better to a point, but then it starts getting worse again. Okay? So the best model is where the error on new data actually achieves a minimal value. And that would be the model that ideally we would be able to discover. Okay? I should note in passing that if you select models that have not yet gotten to that sufficient level of flexibility, we call that underfitting. And if you overshoot that best fit model and you pick a model that's too flexible, we refer to that as overfitting. Okay? So if it's a too simple model, it's underfit. If it's too complex a model, it's overfit. And our goal is to find, of course, the best fit model. The problem with doing that, of course, is that to find the best fit model, in some sense, you may think, well, we need that new data, right? In my previous example, we had those red points. Those red points were data that the model had not yet seen. That's an entirely new data set. And if the answer is, well, just go out and get new data, that's really not much of an answer, because data tends to be very expensive and hard to get and that kind of thing. So getting new data is not a satisfactory solution to this problem. A better solution is to hold out sets of the data. Okay, these are usually referred to as validation sets. So the idea is going to be that we'll take our data set and we're going to break it into two pieces. One of the pieces we're going to allow the model to train on. It's going to get to see that data. It's going to learn from that data. And then it's going to actually make predictions on the data that it has not yet seen. And we're going to use that error to measure and to compare between two different models. We'll use the error on the data that the models have not yet seen, and the best one will win. So the model that has the best error on data that it has not yet seen, that's the one we're going to declare to be the winner. Okay? Now, in practice, we actually do something slightly different than that. That's the basic idea, but here's a better strategy. I'm not going to break the data into two pieces. I'm going to break the data into K pieces, or in general, break the data into something like 10 different pieces, okay? And I'm going to cycle through those 10 different pieces, and I'm going to use 90% of the data, say, so 9 of the 10 pieces, to train the model, and then I'm going to use the remaining 10% to test it. Then what I'm going to do is I'm going to average those test residual sums of squares. So I'm going to average together the different prediction errors on data that the models have not yet seen, so I can get a stable estimate of the error on data that the model in general has not seen. Okay? Visually, it would look something like this. I have my entire data set, listed 1 to 20 in rows. Okay? I'll permute the rows, and usually I'm permuting the rows just so I can enforce some kind of random sampling. If there is some order to the rows that's not meaningful to the problem, but the rows are in that order, I would definitely want to permute the rows, so just shuffle the order of them. You do have to be careful if you have time-dependent data, because the shuffling can actually break that correlation structure in the time, and that can be a bad thing. Nevertheless, in general, what we're going to do is we're going to shuffle the data, and we're going to split the data into 10% and 90%, okay? We're going to train the model based on that 90%. Actually, we're going to train all of the models based on that 90%. So these are the competing models. And then we're going to test them on that last 10%, okay? But as I said, in practice, we're going to do this 10 times over, and this is the process referred to as cross-validation. So we'll first do this on the 10% that it has not yet seen. So the first 10%, we'll train it on the other 90%, okay? And then we just change the 10% each time, okay? So there are 10 different ways that we can do this because we broke the data set into 10 pieces to begin with. So each 10% that gets left out, that's going to get tested, and it's going to give its own residual sums of squares. So at the end of the day, we'll have 10 different residual sums of squares measurements, and the idea is that we're going to compute kind of like an overall measure of the quality of a model, which is going to be its so-called cross-validation error. Okay. Notice that we have in the subscript here, this in parentheses 10. That's to signify that this is tenfold cross-validation. There are other kinds of cross-validation that I'll mention in just a moment, essentially just different numbers there instead of that 10. Okay. Nevertheless, it's going to be the average residual sums of squares across all of the different sets that we've looked at. And then the idea is going to be that the best fit model is the one that has the smallest cross-validation error. Okay. I will say in passing that usually we use the mean squared error, the biased version of the mean squared error for this. But since these are going to be proportional to one another, and since we've been talking more about the residual sums of squares, that's the way that I presented it here. Okay, so cross-validation, in general, the idea is going to be we're going to look at model assessment with an eye towards the data that the model has not yet seen. We've seen that training error on models can be taken arbitrarily low just by making your model more and more flexible. And secondly, we're going to use tenfold cross-validation as our standard model selection strategy. As I said, you can use other kinds of cross-validation, like fivefold cross-validation or leave one out cross-validation, where you're leaving every individual observation out, fitting a model on all the rest, and computing your cross-validation error that way. Obviously, that's a very computationally intensive process, but cross-validation nowadays is a standard tool for model selection.